So welcome to this session late in the afternoon. I realize I stand between you and drinks, so it's really nice you're actually here, not already down there waiting to fill your glasses. So as Deidre said, my name is Christoph Schuber. I've been at Sun for 11 years now, working mostly in security. I'm working in the Solaris security organization. And what I'm presenting today is technology that's been in Solaris for a while, but it's not as extensively used as we would wish. So I'm presenting in this deployment track here basically technology on role-based access control and the cryptographic framework, and show you some examples, some interactive examples of how to use this technology as you would deploy or configure it. I have a third, hang on, make sure this switches, a third section in this talk here, and I'm happy that I can actually draw on some of my colleagues to give you some insight into some of the ongoing security projects on OpenSolaris.org. So there are three topics here: FMAC, Flexible Mandatory Access Control. What's behind this acronym is basically type enforcement and the attempt or the investigation to see what it takes to marry type enforcement with the existing security features in Solaris. Then the cryptographic framework use in ZFS, a very exciting project that's very far along. So I'll have Tony here come up and speak about that and give you a little demo of it as well. And then finally, validated execution, which is also something that's already very far along. And Scott Rotonda will come up and talk about that. So let's jump right in. So what is the problem that we're addressing with role-based access control? Well, it's actually all about the principle of least privilege. So traditionally in Unix, there was this big division between the root user, the almighty super user, and normal users who, could basically do anything in the user space they were authorized to do, but nothing that really related to system administration or really dangerous tasks on the machine. But that model is far too coarse-grained. So there are multiple mechanisms in Solaris that help you to deal with this particular problem in a much more fine-grained fashion. The one that I'm presenting today, role-based access control. There's another one that I won't have time to go into today, and that's the Solaris Privileges model, so process rights management. I want to say just a few words about it because I'm skipping sort of the entire detailed presentation on privileges. So first off, the principle of least privilege, as it says here on the slide, basically says that everything that runs on the system should run only with the privileges it really needs to do to get its job done, not more. Why is that? Well, if in some fashion the program misbehaves or the user misbehaves, they could do damage beyond what they're actually allowed to do, right? So causes for this kind of misbehavior can be malicious. So it could be someone breaking into a system, someone using a buffer overflow to break into a web server remotely, and then executing an interactive shell, for example. That would be really bad, right? But it can also just from faults, hardware faults or any type of software faults that just accidentally get triggered or under certain conditions get triggered. So in both these cases, no matter what the intent, what the origin of the fault was, if it was malicious or accidental, the same mechanisms help to protect you. So Solaris Privileges, so the process rights management works as follows. Rather than have just the division between the almighty root user with user ID 0 and regular users who have not 0 user ID, we break up what actually needs to be, well, the capabilities, the privileges that a program needs to have into very fine-grained privileges. So, for example, the ability to run dtrace on the kernel, or the ability to read a file in the file system, or the ability to fork, the ability to look at another process state. Okay? There are currently about 70 of these privileges. And it turns out if in the traditional model you had root, you would have all these 70. But if you look carefully at individual programs that are out there, just a very, very small subset of these are actually used. even processes that traditionally run as root, they only need 2 or 3 beyond what's called the basic set. And the basic set are just 5 privileges that are equivalent to the power that traditional users needed. So these would include, for example, fork or exec. Good. So this is the other mechanism that allows you to implement least privilege. The one that I'm talking about in this talk is role-based access control. And this is much more interesting from an administration, from a deployment point of view. So what's happening here? Well, role-based access control is actually an idea that goes back a number of years and has been used, employed in different type of systems in computer science for a long time. So in database systems, for example, role-based access control has been used extensively. And the idea is as follows. You define as part of a role certain abilities that someone who wants to assume this role has to have. For example, the example that I have in the slides here, it's a little small to read. You might not be able to read it on this slide, but it's coming on future slides as well, is printer management. So if you need to manage a printer, there are just certain things you have to do. But not everybody in your corporation, in your university, needs to administer printers, right? And you don't want to give someone who needs to administer printers now the ability to log into this big server as root, because he could do so much more with being root. So with role-based access control in Solaris, what you're able to do now is you can define a number of profiles, and there are actually almost 100 profiles already predefined in OpenSolaris, such as the one with printer management here, or backup operator, disk operator, ZFS administrator, for example, right? So you would define these profiles, and together with this profile come basically certain authorizations that source code checks, and I'll show you a few code samples so you see the mapping all the way through from the source code to the administrative databases that maintain this policy information. And also the kind of programs that are actually run to execute these kind of administrative commands. So in this example here with printer management, you see that there are a number of authorizations listed on the right-hand side. So Solaris admin printer read, modify, delete. These would be checked in the source code through the policy databases against the current user who is running, if that user has actually assumed that role that allows him to have these authorizations, as well as the mapping with specific commands with security attributes. So for example, the LPQ command would be run with an effective user ID of LP, so line printer user. So what this picture shows you is sort of the relationship between these different elements. So the role designations, the rights profiles, the authorizations, and how all that is mapped to a user. In OpenSolaris, it's actually very important to understand the concept of users and roles. For administration, it's especially important because root is no longer a user account in Solaris, in OpenSolaris. It comes by default as you install the live CD, and if you've played with it, you already have seen this. It comes as by default as a role. So root is just a role. It's not a regular user. You cannot directly log into the root account. You can switch that role to become a regular user again, but that's really discouraged. Why is it actually an advantage to do it this way? Well, the big advantage is that different users, as they assume the root role, still all their actions get logged as that particular user. So you have full accountability of who did what. So if something went wrong, something was misconfigured, you now know exactly who did this at what time. You can go back and ask, oh, why did this happen, and find out sort of the rationale. And that is a lot better than just seeing, oh, root did this. Oh, okay, well, we have 7 administrators who have the root password. Well, now I'm not any smarter, right? Good. So this slide here shows you a few more details on authorizations. So they're basically unique strings that represent the user's right. And these are tested in the source code. They're defined in a database. You can look at this file, etc security auth_attr for attribute. And there's one library function, namely check authorization attribute, that is sprinkled throughout the source code that now basically takes 2 parameters at important points in your source code. The first parameter is, well, which authorization do you want to check? And the second parameter is, well, which user is currently executing this? And then this library function goes through the mapping, various different configuration files that contain the policy, and determines if that user is currently in that particular role, if he's allowed to assume that role, and if that role has a particular profile assigned to it that then has that particular attribute, this particular authorization. So all of that is hidden underneath that one library call. So here you see just a snapshot of just a subset of the lines in this database. So let me just highlight one because it's a very important one, and that's the second one that's listed here. So Solaris.grant, that is the authorization that someone would need to grant other authorizations. So this one is very, very powerful. So normally very few people would have that. So if you're, for example, the ability to assume the profile of primary administrator, then you have Solaris.grant. I'll show an interactive demo in a few minutes that sort of illustrates both of these concepts again. So the concept of profiles and the concept of the root role. And it shows how they can interact, how both of them allow you to do administrator-type functions that are very powerful, including taking it away from yourself, but then not being able to give it back to yourself unused unless you use the other mechanism, namely assuming the root role. There are a number of administrative tools. There's also some GUIs that you can use for administering these features. Now, I don't use GUIs, so I'm going to show you everything command line. So, good. The programs that you need to use here are usermod and rolemod, and I'll show you some examples in the demo as well. Then, what are the databases that actually maintain the policy? Well, they're all flat files on a standalone system, but they can be backed up by LDAP, for example. So you can configure and contain all your policy in LDAP, and then the individual systems that sit on the network draw the policy from LDAP. That's actually the typical deployment you would see in an enterprise or at a university, any type of bigger, larger organization. So the first database here that I'm listing is policy_conf, and that maintains the policy on a system-wide basis. So that is always consulted first. If you configure something in here for users, it's valid for all users, for example. And then the next one is the database user_attr, and that one maintains the information for individual users on this system, as well as for the roles. So what I'm listing here, this entry at the very bottom that says root : type equal role, that shows you that root is actually not an account on this particular system, but it is a role. If you switched it over, it would say type normal, and then it's actually a user account. And it lists the authorizations that this particular role has. So it says Solaris.star, which means all of them. And I just looked it up on the release that you're getting. There are about 230 authorizations specified. So it's fairly fine-grained what you can use in your source code, too, to check which type of authorization someone actually needs to do a particular function. And there's nothing in your way to augment that and define additional authorizations if you find that what you have here is not fine-grained enough. Good. So, rights profiles, already mentioned that. It's basically a mechanism that helps you and allows you to bundle together these different commands and the authorizations. So if there's one thing you should remember from the discussion around RBAC, it's actually that entity relationship diagram that I showed earlier, where you had the mapping from user to role, from profiles to role, and then the two arrows of the two elements that fed into the profiles, namely the commands from the bottom and the authorizations from the right. Good. Few more policy entries. So policy_conf. Already mentioned that user attribute I mentioned, and then profile, so prof_attributes, that defines all the different profiles that are predefined on the system. And again, you can extend that to your heart's content. The ones that are in there are very typical ones that users and enterprises actually use. So the one I'm listing here is, again, the almighty one, the primary administrator. And there's a comment field that basically says what this particular attribute the profile is all about, namely can perform all administrative tasks, and then it again lists which authorizations are given to this particular profile, again Solaris.star, so all of them, in particular Solaris.grant, and then a help page, HTML page pointer that can be used for finding out more information about it. So all roles are based on rights profiles, and users can change into particular roles, assume roles by using the SU command. So typically now, if you are installing OpenSolaris the first time on your machine, as part of the installation process, you're asked to type in your user ID, your password, and also a root password. Now, that is the password that you need to assume the root role. So as you're logged in as that regular user, by default, that first user that you're installing is actually able to assume the root role as well. And we'll see in the demo in a minute that this is listed in the attribute entry for that particular user in the database as well. Users can also use what's called the profile shell, or pfexec, two different things. But what it basically allows you is to precede your commands that you want to execute with higher privilege with pfexec, and then pfexec does basically the mapping for you and goes through the various different profiles and database entries to see if you are indeed authorized to go assume that profile. Good. This is just the script of the demo, so let me sit down and show that to you. I put it in the slides because you can download the slides, and it's much easier for you to go back and look at it at a later time. So what you see on the screen now is a running instance of OpenSolaris 2009-06 inside VirtualBox. I'm running this, so what's on the hardware is the same operating system, but I'm running the same copy again in VirtualBox. The reason is I can make all kinds of modifications to this, then blow it away and start at the snapshot where I was. So that's kind of nice that I don't, change system configuration on the running system, yet can still show you very powerful concepts, right? What's also running or installed on this system here is a little demo script that I wrote, where basically it pretends to be typing while I'm speaking to you and have my hands up in the air. So that's kind of cool, no? I love it. Because, I mean, in this example, you can't really see it that much, but sometimes in these demos, you have very long command lines with, hundreds of arguments, not quite. But for me to type them at the same time while I'm speaking, even remembering what to type, is rather hard. So my brain is not big enough for that. So I'm logged in as user JDoe here, and let's just look at which profiles are assigned to this user. So this is really a very virgin installation of 2009-06 out of the box. So these are the profiles that the default user gets. And this is, first off here, primary administrator, and then a number of other ones. It looks actually like a rather long list, but if you look at them carefully, there are very fine-grained operations like suspend to RAM, suspend to disk, brightness control, CPU power management. So things that you would actually expect a regular user to be able to do. Good. Then let's look at the authorizations. And we have Solaris.star, which means this particular user is actually all-powerful. Why is he all-powerful? Well, because he has the primary administrator profile as part of his profiles. You wouldn't expect that from other users on an account, right? This is basically one of the super users here. So let's look at the database, the policy database entry for this particular user, so user_attribute. And I'm just listing the one line that belongs to this particular user here, John Doe. And you see two important things. First, oops, I'm highlighting too much here. First, the profile primary administrator. So this is the first part that I'm demoing here. And also the role root. So he can also assume the root role. So he has two ways in which he can become an administrator. Good. Let's use the usermod command to change the profile entries for that particular user. So what I'm doing here is I'm executing usermod under pfexec, which means use the profiles mechanism and reset the list of profiles for user JDoe to everything that's standard for a user account other than a super user. So what this will do is it will actually take primary administrator out of the remaining list. Okay? So let's just double check that. We look at the same entry again. And we see that now it says type normal, so it's a normal user account, but the profiles entry disappeared. Right? So if I look at the authorizations, it looks like a very long list of authorizations now, but it's actually rather short. These 20, 30 entries here, whatever they are, they're by far not Solaris.star, the 231 that are actually defined on the system. Right? This is a very, very small and innocuous list. Let's try to give ourselves, so JDO, that profile entry back. And this should fail now, because pfexec, if you remember what I said earlier, goes only through the profiles entries. It does not assume the root role to do anything. So indeed, it complains, error permission denied, and the permission is denied because we have no way with the remaining authorizations and the remaining profiles that this particular user belongs to give ourselves back this very powerful primary administrator profile. Let's check the authorizations. Well, there's no grant authorization in here anymore. So we cannot even give ourselves back others that we would need to modify our profiles entry here. Okay, well, it seems like we're stuck, but we're not. The thing that's still highlighted on the screen here is roles equal root, right up here. So we can now assume the root role. Now I actually have to type something. And execute that same command from earlier again. This time we don't need to go through the profile shell, so no pfexec here, because we are root now. We have assumed the root role. And we give that primary administrator profile back to the user. It always warns us that it might not take effect until the next login, but in this case it actually does. So you can ignore the warning. So let's exit this and double check again. So we'll look at the policy database entry for the user. And voila, there you see, profiles primary administrator is back. We'll check the authorizations, and we have Solaris.star again. So this should give you a flavor of how to use role-based access control, what the relationships between the various different elements are, what is already predefined, and where the points are where you can extend the system, where you can configure them, such that the system does exactly what you need for your particular task. How is this check auth attribute actually used in the source code? Well, I mentioned earlier it takes two important attributes, arguments, namely the name of the authorization as a string and the name of the user. So the code looks very, very simple. Traditionally, the code looked like this, right? You checked if the real user ID right now was 0. If it was 0, good. If not, raise hell. The code with checkauth adder doesn't look much more complicated than that either. All you need to do is you need to retrieve the entry from the password file or database entry if you're an LDAP or other databases behind it. Then once you have that, you look up the username. So the password pointer entry, the reference to the password name, is the argument that you need for the username. And the first one is the string that you actually want to check against. In this case, solaris.jobs.admin. And that comes back with a true or false value. So if the authorization is granted, you can continue at this point. If not, if it returns with false, then you abort at this point because you don't have the right authorization. So this is the final slide in the section on RBAC. So I mentioned earlier the other mechanism to implement least privilege is the Solaris Privileges, so process rights management. And I just wanted to mention that they are really complementary and compatible. They are used in different places in the system, right? If you want to do very fine-grained control of what is the capability of a particular program with respect to which kind of actions it can take, you would use the process rights management and Solaris Privileges. If you're more focusing on deciding which kind of higher level actions, programs, administrative tools a particular user can use, then you would go to RBAC. So rights profiles, privileges, and authorizations, they can be directly assigned to users, and privileges and authorizations can also be directly defined to roles. What I also should have mentioned on this list is actually that profiles in OpenSolaris now in the current release and going forward are hierarchical. So you can make profiles sort of entries of other profiles. So they would translate through and basically assume sort of the entire transitive closure of all the profiles that are part of this hierarchical tree. Good. The next section here is the cryptographic framework. And that is a system that was introduced in Solaris 10. And it solved lots of problems. And rather than just listing all the problems, I'm listing here sort of the motivation. It's sort of the other way of looking at it. So first off, cryptography, a lot of people when they hear security, oh, what do you work on? Oh, I work on security. Well, they first mention viruses, and if they're a little bit more knowledgeable, they mention cryptography, right? Well, I don't work on viruses. I don't work on antivirus software. And, well, I've dabbled in cryptography, but again, my brain isn't big enough for cryptography. But cryptography is really a building block, a basic building block in computer security for so many other services. So if you look at network security, the traditional way of securing communications is always based on cryptography. So both in the user land and in the kernel, there are actually lots of protocols that use crypto. And I'm just listing a few here. So in user land, SSL, SSH, generic security services, so it's sort of the access layer, Kerberos, IKE, PAM, you name it. In the kernel as well, IPsec is in there, for example, various Wi-Fi drivers. LoFi encryption, the kernel-based SSL for acceleration of things that can be done in the kernel, for example, kernel-based web servers and whatnot. And there were lots of problems over time with respect to having duplicate implementations, multiple libraries that implemented the same type of algorithm. And it was very hard to keep these things up to date, keep all of them patched, fix all the bugs in the various different instances. And it just contributed to totally unnecessary software bloat. So these problems with versioning and software defects are all addressed with the cryptographic framework. And it just contributed to totally unnecessary software bloat. So these problems with versioning and software defects are all addressed with the cryptographic framework. And the basic architecture is really simple and is one that is applied actually in lots of areas of computer science. So you build a framework that has two layers of interfaces, one above and one below. And the one above is the service interface that allows any consumer to consume the cryptographic services that are provided by this particular framework. And that is not just encryption, decryption algorithms, but also basically everything crypto-related. So that includes key generation, for example, random number generation. That includes message digests, digital fingerprints, right? So all the basic building blocks that you would really expect from a comprehensive cryptographic framework. Well, that's one of the interfaces from above, so for the consumer. But there's also a provider interface from below. So, and in this provider interface, both of these interfaces are published and open. You can plug in any type of software or hardware provider that you want to make available through this particular framework. So you would plug in, for example, a software implementation of AES, of triple DES, a software implementation of SHA-256, a software implementation of a random number generator, right? X19 or whatever they're called. And you make these interfaces pluggable and the framework configurable in such a fashion that you can have not just a single implementation available to the framework, but multiple. And this is very interesting. Earlier I said you just want one implementation, right? We're building this framework so we don't have multiple competing ones. And now I'm saying one of the features is that you can have multiple. Well, why is it actually interesting to have multiple? Well, because some machines have actually hardware acceleration for certain functions. Others don't have that. So you typically provide a software implementation, and the system ships with the full software implementation framework of all popular algorithms, and I'll go through the list in a second. And Certain machines have crypto hardware acceleration, either because the CPU gives it to you, or you've plugged in an additional board, or some additional crypto acceleration hardware that's available on the machine. And then you can configure the system either manually, that you say, oh, I want to use this particular key store because I trust this hardware more than my software implementation. Or you say, oh, I let the machine choose whichever the best one is. And there's basically a definition of, well, if you have a hardware provider, then that's better than a software provider, right? So that would be transparently made available. Good. So lots of new features are added to the crypto framework. Although it was initially created and installed or distributed with Solaris 10, lots of progress has been made there, and a big part of our group is working on a day-to-day basis on making it even better. So for example, ECC algorithms were recently added. Then whenever there's new hardware that Sun ships that needs to be supported, we add the necessary drivers to that. But because it's open, other governments or other companies that have their own cryptographic hardware can plug that in as well, and it's as easy as writing a device driver for that particular hardware to make that available. And you have lots of source code to look at to see how that is actually done. So very nice. So typical consumer-producer architecture. The next few slides I'll go through a little faster because this is part of the demo. So all the gray shaded background slides, as I said earlier, they're just in the slides for your reference if you want to look at it afterwards. So terminology, I already went through most of this. What's important is that the interface that's made available to the user, so the service interface from above that I mentioned, is actually PKCS 11 based, version 220. So that means there is a standard interface, the predominant standard interface for software to use. So you don't have to have the impression that, oh, if I want to use Sun's crypto framework, I have to do lots of work to port it and actually take advantage of that. No, a lot of software today already out of the box uses PKCS 11. So all you need to do is link it against the right library and you're done. If you have software that uses other types of libraries that are also very popular to provide cryptographic functionality, such as OpenSSL or the Netscape NSS stack, you can also use the cryptographic framework. And that's very transparent for you as well, because those type of libraries, OpenSSL, NSS, they provide at their bottom end the ability to use PKCS 11. So it's a fairly straightforward slight overhead mapping from OpenSSL to PKCS 11 to using the cryptographic framework. And if you're a Java programmer, if you ever used JCA or any of the cryptographic functionality in Java, you're also transparently using the crypto framework because that is the provider underneath that's plugged in. Which, if you think that through now, is really cool. You write your Java program, you run it on a Sun machine. It actually takes transparently advantage of any hardware acceleration that might be in that cool Sun box that you just bought, right? Or that someone else bought that you're using. So, very powerful architecture and how it's all layered together and how it's transparently delivered to you. Good. There are two halves to the crypto framework, the user piece and the kernel piece. Depending on where you program, you would use one or the other. In the user space, it's basically PKCS 11. So PKCS 11 shared object library, that's your friend. And if you're operating in the kernel, the interface is PKCS 11-like, but not exactly the same. The crypto framework itself is managed through the service management facility. So all the various different modules drivers are loaded as part of the system startup, which is very nice as well because that means should any of these components fail, they are through SMF now tied into this high availability framework such that dependent services are automatically restarted and the system just keeps providing you the crypto functionality, although something might have fatally crashed in between and just is getting brought back up by SMF. All right, let's go through the demo and look at a few of the user-level commands, and that should give you a flavor of the crypto framework. Good. So I'll sit down again and show you the second half of the demo here. Where are we? I not in the? That's why. See, that's why I have a tool that does the typing for me. So first, let's list what's available on this system. Well, this is OpenSolaris 2009-06 running inside VirtualBox. So I have only software providers on this laptop. I grabbed this out of a pile of laptops on Friday, installed everything from scratch. There is no hardware crypto provider. So what you see are the user-level providers, which are basically the two shared libraries for the PKCS11 the functionality. And then it lists which kernel software providers are also available. So a number of the well-known algorithms that you would expect, DS, AES, ARC4, ECC, number of message digest, SHA-1, MD4, MD5, and a software random number generator. Kernel hardware providers, well, that line is kind of empty, so nothing installed on that particular machine. Excuse me. If you look at the man page for PKCS11 soft token, it shows you all the mechanisms that are defined for the crypto framework. So it shows you all the algorithm and mode combinations. So let's pick one. You can use DES as a key generator. You can use DES in EBC or cipher block chaining mode, CBC, and as well padded. So a long list of those. Let's create a message digest. So first, let's look at which digest algorithms are available. So it lists SHA-1, MD5, and SHA-256, 384, and 512. And let's create, just for kicks, the SHA-256 of the password entry. And there it is. And if you're really fast at calculating in your head, you can verify this is true. Anyone? OK, we'll just assume it's right. Then we'll look at the encryption algorithms. And with -L, you see not only the encryption algorithms listed, but also the minimum and maximum key sizes. Now, not all values in between make sense, right? You can't run AES with a 133-bit key. You can run it with 128, 192, and 256. But it gives you the extreme values. And we just assume if you're using these libraries, you have some basic understanding of what cryptography is. Then let's use pktool to generate a key. And I'm doing the same exercise now twice. So I'm generating first an AES key and store it in a local file. So this would be the key store. And then I'm using that for encrypting, actually, Etsy password. Then I'm doing the same thing again, but I'm using the soft token implementation on the machine. And the nice thing about that is it's also persistent across reboots, but it doesn't have a trace, an easily accessible trace in the file system of a key database that just happens to lie around in your home directory or wherever. So I generated the key. Now I'm encrypting with that particular key the Etsy password entry. And I'm dumping that to the screen. And this certainly looks encrypted to me. So you just have to take it on my authority now that this is indeed AES encrypted. Let's put it this way. If I decrypt it with AES, the initial password file comes back out. So let's look at the tokens. So there is one soft token defined on this machine, namely the default one, Sun Software PKC11 soft token. So let's generate now a key that we store in that token as well. But before I can do that, I actually need to change the PIN, because this is a brand new installation. So the default password, which is also listed in the man page, is change me. I hope I didn't mistype it now. And I'm putting in a new one. OK, passphrase changed. Now let's generate the key. So pktool gen key. Where is it being stored? In the soft token. This time I'm generating a key of type triple des with key length 192, and I name it key 2. So now I need to provide the PIN. Good, it's generated the key. Let's look at the list of keys that are actually in the token. There should be just one in there, namely the one I just generated. The database was empty initially. Good. And you notice every time I do an operation that involves the soft token now, it actually requires me to type in the PIN again, to access it. So there's the access control for you. So there's the key number 1, triple desk, called key 2, 192. And then I'm using that key again for creating an encrypted version of the password file. So the input file is etc password, the output file password2.enc. Again, I need the password for token access, and I dump the encrypted version onto the screen. It'll look different now than the previous one because I used a different algorithm and I used a different key that I had newly generated. And again, you have to take it on my authority that this is actually encrypted and not just, some random blurb. Good. Let's switch back to the slides, because I promised you a third section here. And this third section has some interesting ongoing projects. FMAC is the first one, so just sort of the highlight here on FMAC. This is a project that's been going on for quite a while. You might have heard of selinux. Selinux is the prototype version of type enforcement built into a Unix operating system. And they've made quite some progress, and it's used in lots of interesting places. So already, oh gosh, it's probably been a year and a half or even longer than that ago, we started a project at Sun as part of OpenSolaris, actually, as a joint project between the NSA and Sun, investigating what it would take to put type enforcement in a compatible manner into OpenSolaris. And this is actually a really difficult task. The promises that type enforcement have are grandiose. At the same time, there are some real trade-offs with respect to how easy is it to configure, what would be the performance impact, which customers actually care about. So it's far from, oh yeah, cool technology, let's put it in. It's more, well, let's really look at it carefully. Scientifically, it's very interesting, but does it make sense in the greater environment? So the main driver behind this, I'm not sure if he's in the room. Can you wave if you're here? No? He's in the OpenSolaris booth downstairs, demoing something completely different. So if you want more information on that, you can talk to me afterwards, and I can also point you at John Weeks, who is downstairs. So very cool project. They've made lots of progress. If you want to get involved, if you're interested in this, here's the URL. So opensolaris.org/os/project/fmac. And on the OpenSolaris pages under the security area, you find actually dozens of other projects that are going on. These are really just some highlighted ones. The next one here is ZFS encryption. And here I'm happy to introduce Tony, who is getting a lot less time than I thought I could give him.
No problem. My name's Tony Scarpino. Work in the crypto group in Solaris and worked on the ZFS crypto project. And so ZFS Crypto, basically the idea, you want to get your ZFS data encrypted. You want to get it secure. So what we set up was to have the encryption policy based off of data sets. Most systems, they may have 1 or 2 pools. You don't want to have it at the pool level because then you just don't have a lot of flexibility. So you set up and say, okay, I have my laptop. You don't want to sit there and say, I have to create another pool. What, I'm going to have to put in a USB drive or break it and mess up my drive and stuff? No. Maybe you're going to have your server, maybe with another pool. You say, okay, well, I'm going to have that one be encrypted. I'm going to have my R pool be unencrypted. And I'm going to delegate based off of all the ZFS allows and all the ZFS permissions. Say I want to be able to allow these certain directories to be encrypted, these other certain ones not, and also allow maybe users to have individual individual keys and stuff, and being able to have their own private areas. So in the initial design, we have AES 128 and AES 256 CCM. The design allows for future algorithms to be added. If you're trying to encrypt, or if you're trying to transport, say you're having an iSCSI or fiber channel over Ethernet, or you're coming off of the network, basically, you can have like your ZVol on that external machine encrypted, and then using IPsec, bring that over onto the machine and have your users be able to access that. And in this initial setup, we don't have the ability to boot off an encrypted data set. You can move our temp and have that as a separate pool, or sorry, a separate data set. Temp temp can't be encrypted, but you can allow to have a ZVol that will add an swap file to it and be encrypted, and no encrypted core dumps. Key management. So wrapping keys. The keys are basically inherited basically from the data sets and from the pool. So you can, if you set it up at a higher data set and you say, I'm going to have this encryption key, and then following data sets will inherit that encryption, the same key, the same key scopes, whether it's a passphrase or a file, or further, encryption keys. It'll inherit a lot of this stuff. This encryption, although, needs to be set at creation time, because you don't want to have problems with the copyright rights and situations that is on the next slide. And you also can go through a change key where you can modify the keys and it can be switched over that all new data will be using this new key and inherit the old one. And let's say key phrase, passphrase, prompts, HSMs and key scopes, and HSM or smart cards. And then the final slide here is basically talking about how you set the encryption creation time. The actual key is randomly generated. It's not a key that you provide. The key that you provide on the command will actually wrap that key. And like I was saying, this is set at encryption time because you don't want to run into the encrypt later problem, where you have a whole bunch of clear text, and you don't want to have the clear text be sitting there meanwhile you start encrypting with all new text. That's not going to be encrypted, so that's why you start it that way. And finally, that's the bottom there is our website you can go to get a lot of information and check out the progress of the project.
Great. Thank you, Tony.
Thanks.
Good. Before someone jumps up here and wrestles the microphone out of my hand, I'd better wrap this up. We're out of time. We have one final project that we wanted to present here, validated execution. Let me just say it's really cool. It basically allows you to validate any type of program, binary, kernel, scripts, even utilities, configuration files, with cryptographic means before they get executed. And this is all tied into the trusted platform modules on Solaris as well. So once that is complete, you can really have complete trust in that what you're running is indeed what was configured, installed, and what you want to be running. Still not said that it's completely correct, but at least you're running what you think you're running. So finally, a slide that has some pointers of where you can get hold of us. So you can always send me an email at christoph.schuber@sun.com. You can check out the blog page. But the best resource for you probably are the OpenSolaris.org pages in the security area. Thank you so much. And if you have questions, I can probably take one question in the remaining -3 minutes. Please use the microphone because this is recorded and broadcast. Oh, I'm getting no questions. Okay, good. We'll take the questions offline then. Sorry. Thank you.